and there's some level of course or some number of courses which are also running beyond this course. This is the first course for this academic year, and there are other courses also which would be running in the coming months. So if you plan to attend those courses also, you can also register for those courses which are, and the information of all those courses is available on IIT Mandi website. So once again, welcome all of you. So first of all, I invite Professor Akilan Tiwari to facilitate our speakers, and Professor Kanat. Yeah. Yeah, Hank, you said I'll call you. So this is Himachali shawl with Himachali topi as a local uh, gift. So it also has a logo of IIT Mandi also. So because they also plan to travel to. Yeah, now I call Professor Hank. Yeah, please. Yeah, please stay on the stage. So that. So this will also help you when you travel to Parashar because it would be quite cold. Yeah, thank you. Yeah, thank you, Professor Agna. Yeah, please have a seat. So the schedule is shared with all of you, and there are certain instructions, there are guidelines which are also available on the website. So in fact, if you turn around your ID card, so you would see very quick instructions also, because you might have seen that IIT Mandi do not have the boundaries. So it is good, and also it is we are close to the river. So and here the flow of the river can go turn into a high tide anytime. So be careful. Do not go to the river side, at least in this 1 week. Even if you want to go and explore, okay, take the permission from the security guards, because generally it is the what we have seen in the earlier that no boundaries, the river is closed, so people want to explore, but always explore this with a safe mindset. So I think we can start with the course. We have all the students and participants attending the course. So we'll start with the day one. Yeah, thank you everyone. Thank you.
Thank you for the very nice introduction. For being here today. Can you all hear me well, also in the back? Very good. Yeah, so we're going to present this course on database systems and control. I will present day one, and then Kanat will take over in day two, and we alternate like that. So for today, I just want to start by explaining to you the contents of the course, giving you a historical perspective. So I want to explain the contents of the course. Many of you have followed the course in linear. There you're very familiar with building controllers and analyzing system properties of way of designing controllers for a physical system. A procedure. Can you hear me? Yes? Okay, great. So I want to explain the contents of the course using this figure over here. And what I was saying before, imagine the situation that you want to design a controller for a real physical system. And typically what you would do is you would first create a mathematical model for that physical system, and then using model-based control, you would obtain a controller. Alternatively, if you're maybe not interested in designing controllers, but you want to assess certain properties of this physical system, like stability or controllability, you would also use that mathematical model, and through model-based analysis, you would assess that system property, right? Whether your system is controllable or not. Now, the point is the following. Of course, these mathematical models of dynamical systems, they do not come falling from the sky. Somehow we have to create a mathematical model of a physical system before we can do control design. Now, there are different ways of creating mathematical models. You could use first principle models. So using physical principles, you obtain a model for this physical system, using Newton's law of motion, for instance. Alternatively, you could also use data to come up with a mathematical model. And that process of going from data to the mathematical model is called system identification. So one approach of doing this whole pipeline then for a physical system to obtain a controller would be to first collect data from the physical system, use system identification to create a mathematical model, and then use that mathematical model using model-based control design to finally obtain a controller. We call that an indirect approach to control design. Indirect in the sense that you go through the step of system identification and modeling to finally end up with the controller. Now, what we want to do in this course is what is known as a direct approach to data-driven control design, meaning that we want to take the data from a physical system and directly synthesize a controller using that data. And we call that direct data-driven control design. Similarly, if you are interested in properties of a dynamical system, as I said, like stability or controllability, we're also going to consider direct data-driven analysis. So we first collect some data from a dynamical system, and then directly we assess whether the dynamical system has these properties or not. So that's the idea. We want to kind of avoid the system identification process and the modeling to come up with the controller. And instead, go directly from data to controller. Now, let me say a few words about the motivation for that pipeline. Now, first of all, we live in an era of big data. Data is widely available, and the question of how to use that data for control design is a very relevant one. Secondly, the systems in engineering are becoming more and more complex. Which means that maybe only modeling from first principles is not enough to achieve the performance for such complex physical systems that we want. For instance, in the Netherlands, where we come from, we have this company called ASML. They build very large chip machines that they distribute to the main manufacturers like TSMC. And they use these machines to build or to create chips. Now, a single machine costs more than 100 million euros. And the control algorithms in these machines need to be extremely precise on a nanometer scale. Now, I wouldn't imagine one could create such a machine without using data. Then finally, a point about the motivation for using this direct pipeline. So why should we avoid maybe modeling, and why should we go directly from data to the controller? Well, direct approaches are promising in situations where modeling is either challenging or sometimes even impossible or computationally expensive. So as you can imagine, it takes computation time to create a mathematical model from your data. If you can avoid that, that approach will be more computationally tractable. But maybe a more important point is that, and we will see some examples during the course, in some cases, it's impossible to use data to uniquely construct a model for a dynamical system. And we'll see examples that even in such situations, it may be possible to construct controllers from that data. That's a very strong motivation for using the direct data-driven control paradigm. Okay. Now, the outline of the course is as follows. So as I said, today I want to give a bit of a historical perspective. Then on the second day, we'll talk about the notion of data informativity. So that's the topic that we have been working on in the last 6 years. And we'll talk about analysis and design using noise-free data. In the third day, we're going to extend that to noisy data, so where the data are corrupted by noise. In particular, there we're going to talk about the stabilization problem. And in day 4, we consider more advanced topics, like suppose that in addition to stabilization, you also have some performance guarantees that you want to achieve, like H-infinity performance. Or you want to verify dissipativity of a system. And there we also make the extension to input-output data. So in the day 2 and day 3, we will focus on the input state data case. And then finally, in day 5, we'll also use the data informativity framework to treat system identification and also discuss experiment design. So methods to design the inputs of your experiment in such a way that you have good data. So this is a rough outline of the course. Maybe then I can explain a little bit about day 1. So what are we going to do really today? Well, in the lecture this morning, I want to treat 5 topics. So I'll start by the development of subspace identification at the end of the 80s of the previous century. Then I want to talk about an important result called the fundamental lemma, first proven by Jan Willems and co-authors. And that fundamental lemma, that gave rise to a number of data-driven control techniques. And I will highlight some of them, namely data-driven tracking, predictive control, and a way to parameterize closed-loop systems using data. So these 3 methods are basically applications of the fundamental lemma. And then in the afternoon, we have a problem-solving session on these topics. By the way, whenever you have questions, feel free to interrupt me and we can discuss. That holds for all of the days, by the way. So feel free to ask questions whenever you have them. Okay. Good. Well, before I really start, I want to acknowledge also our collaborators. So together with Harry and Jaap, we did a lot of work on the data informativity framework that we're going to use throughout the course. And then with Paulo Rapizada, we worked on system identification and experiment design. Okay. Well, let's start with the historical perspective then. So this is the basic timeline that I want to treat. So I want to start at the end of the 80s, where subspace identification was initiated. So I want to talk about this paper by Mark Monen, Bart de Moor, Lieven van den Bergen, and Joost van der Wallen on and offline methods for subspace identification. And there's something very interesting about this literature. So actually, 15 years later, or 16 years later, after the development of subspace identification, in 2005, there came this result by Jan Willems and others about the fundamental lemma, in a paper that was called A Note on Persistency of Excitation. And actually, that paper gave the kind of fundamental backbone to subspace identification. But what was interesting is that that result was not known in the 80s when people started to look into subspace identification. And so that's an interesting development. There's this kind of gap. So I will talk about this fundamental lemma by Jan Willems and others. And then there is kind of another gap in the literature. So that fundamental lemma was already used by people like Ivan Markovsky and Paolo Rapizarda to do analysis and control design. But it didn't really take off around 2005. But now, recently, around 2019 and 2020, there's this huge surge of interest in the fundamental lemma. And there are many papers that use that result to design controllers using data. And I will talk about these three. Okay. Well, at the moment, of course, I understand that it's not clear to you what all these papers are about exactly, but I want to go through the list of papers and talk about them one by one in the rest of the lecture. So let me start by some preliminaries about mathematics so that we're on the same page. So I denote by n the set of natural numbers, including 0, and I let I and j be two natural numbers. Let's say that I is less than or equal to j. Then I'll define this integer interval from I to j as the set of integers I plus 1, up to j. I will consider functions, f, from the set of natural numbers to Rq. Now, R denotes the set of real numbers. And for such functions, I will consider restrictions to a certain interval of integers. So I will consider the restriction of f to ij. I will denote that by f subscript ij. That is a column vector just considering the evaluation of the function f at I plus 1, up to j, like that. So that's a real vector. Now, for such a restriction of a function f, I will also consider what is known as a Hankel matrix. So what is a Hankel matrix? Well, we have this Fij, this restriction, and I built this matrix over here. So it's a Hankel matrix of a certain depth k. Now, k is a number that is less than or equal to j minus I plus 1. And what is this Hankel matrix? Well, in the first column, we just put fi plus 1, up to fi plus k minus 1. So these are k evaluations of the function f. Now from fi up to fi plus k minus 1. Then every next column in this Hankel matrix is just a shifted version of the previous column. What does that mean? Well, in the second column, we start at fi plus 1 instead of fi. So we shift by 1. We go from fi plus 1 up to fi plus k, like that. And we keep doing that until we reach this point fj in the last entry. Right, so every column, again, is a shifted version of the previous one. So this is called the Hankel matrix, and I just want to point out one thing, namely, I use this subscript k here to denote the number of block rows in this Hankel matrix. So every f evaluation that you see here is q-dimensional, right? So, for instance, fi is in Rq. We have exactly k evaluations of the function f here. So that means that the entire Hankel matrix has k times q rows. Right? Okay. So far, so good. Do you agree with this definition? Yeah. I don't know if there would be much to agree to, because this is the way we introduce a Hankel matrix typically. Yeah? But, okay, using this Hankel matrix, we now also define the notion of persistency of excitation. So I say that Fij is persistently exciting of order k if this Hankel matrix, Hk of Fij, has full row rank, meaning rank equal to KQ, again, because this Hankel matrix has exactly KQ rows. Right, so when this Hankel matrix has full row rank, we call this signal Fij, persistently exciting of order K. That will play an important role in the further development of today's lecture. Okay. So those were some preliminaries on signals and Hankel matrices. Now let's talk about systems. So I'm going to consider discrete time linear systems of the following form. U here is the input of the system, that is m-dimensional. X is the state of the system, which is n-dimensional. And Y is the output of the system, that is p-dimensional. And the matrices that you see here, A, B, C, and D, are real matrices of appropriate dimensions. Finally, T here denotes time, and it's assumed to be a natural number. So time runs from 0, 1 to infinity. Okay, good. How many of you are familiar with the notion of controllability for these kind of state space systems? Great. Yeah, the majority, I would say. Yeah, okay, that's very good. So then you know that we call a linear system of this form controllable, or Kalman controllable, if for every pair of states, x0 and x1, there exists an n and a sequence of control inputs, u0, u1 up to un minus 1, that essentially steers my system from x0 to x1, right? Which means that if I initialize my system at time 0 at this point x0, then at time n, I must end up at the point x1. And I must be able to do that for any pair x0, x1 that you give me. So for any initial state, I must be able to find a control input that steers my system to this arbitrary final state, x1. In that case, we call the system controllable. Well, there's this Kalman rank condition for controllability, saying that our linear system is controllable if and only if the rank of this Kalman controllability matrix is full, is equal to n. So what is this Kalman controllability matrix? Well, it's a matrix B, AB to A to the power m minus 1p. And this matrix needs to have full row rank, equal to n. So this is a very simple check. Given the parameters of the system, you can easily check whether your system is controllable by computing the rank of this matrix. Okay. You note that using this Kalman rank condition, controllability only depends on the matrices A and B, and not on the matrices C and D here. That's why I sometimes say throughout the course that the pair AB is controllable. Again, because controllability only depends on A and B. Okay. Good. Well, maybe a notion that some of you may be less familiar with is the following. So, for this type of linear systems, I also introduce what is known as the input-output behavior of the system. Let's have a look how that is defined. So intuitively speaking, the input-output behavior contains all input-output trajectories that this system can produce. A little bit more formally, what does it mean? Well, the input-output behavior, B, contains all uy functions from n to Rm plus p. Again, m is the number of inputs, p is the number of outputs, for which there exists some state trajectory of the system such that the equations of our system are satisfied for all t. And so the input-output behavior, again, contains all input-output trajectories that this linear system can produce. So using the input-output behavior, I also define the notion of observability. So I say that my system is Kalman observable if for every input-output trajectory of my system, in other words, for every ui in the input-output behavior, B, there exists precisely one x from n to Rn, such that these equations hold for all time t. So for unobservable systems in general, there may be many state trajectories given a single input-output trajectory. But the system is called observable if there exists only one state trajectory for which these equations hold for all time. In that case, we say the system is observable. So what does this mean intuitively? Yeah, it means that using the external variables of the system, so using the input-output trajectory of the system, you can reconstruct the state of the system, right? Because there is exactly one state trajectory corresponding to that input-output trajectory of the system. And so observability means you can reconstruct the state from the input-output trajectory. Well, there is also a Kalman rank condition for observability, and that's the following. So the system that we had above is observable if and only if the rank of this particular matrix, which I construct from C times A up to C times A to the power n minus 1, is equal to n. And since observability only depends on the matrices C and A, we sometimes say that the pair CA is observable, instead of saying that the linear system is observable. Okay. Good. Well, throughout the course we're going to talk about data. And this input-output behavior that we have here is defined on n. So for all time between 0 and infinity. But when you collect data from a system, typically that is just given on a finite interval, from, let's say, 0 to t. So that's why I also introduced this notion of a restricted behavior. So this is the behavior of the system onto a finite time interval. Let's say from times t1 to t2. So let's look at these two integers, t1 and t2. In n, with t2 larger or equal to t1. Then I define the restricted behavior in the following way. So it's all restrictions of u to the time interval t1, t2, and all outputs y restricted to the time interval t1, t2, for which uy is in the behavior. So I look at an arbitrary trajectory, uy in the behavior. I restrict it to this time interval between t1 and t2, and that must then be in the restricted behavior. In fact, the restricted behavior contains all of these restrictions. Now, there are a couple of facts that you can prove for such restricted behaviors. The first one is that this is a subspace. So the restricted behavior on this t1, t2 is a subspace of this space over here. And something interesting is that since we start with a time invariant system, we in fact have this series of inclusions. What does that mean? Well, trajectories on the interval t1 plus 1, t2 plus 1 are also trajectories on the interval t1, t2. So trajectories in the future are also trajectories in the past. And so we have this chain of inclusions. What about reverse inclusion? Is that something you know? Do you think that, for instance, the reverse inclusion here also holds, or maybe not? One needs to think about that, of course, for a bit. Now, what do you think? Can only be two answers, yes or no. Huh? So, well, let's have a look at an example. So suppose that I look at this system. So I choose both A and B to be 0. So it's a very simple system. Let's assume that all variables are scalars, so u and x are scalars. And the output of my system is simply equal to the state, equal to xt. Well, I could, let's see, choose x0 to be 1, u0 to be 1, and then because of this equation also y times 0 is 1. Which means that 1, 1, the input and the output, is in the restricted behavior of the system on the time interval from 0 to 0. Right? This is a valid length 1 trajectory of the system. On the other hand, you see that due to this first equation, we always have that x at time 1 is equal to 0. Which means, due to the second equation, this implies that y at time 1 must also be equal to 0. Yeah, but that then implies that 1, 1 cannot be in the restricted behavior on the time interval from 1 to 1. Right? Because at time 1, always my output needs to be 0. Well, the conclusion is the other inequality here does not hold in general. Sorry?
Will it hold if the system is controllable and in this particular example it was not controllable?
Yeah, that's a great question. So you beat me to it, actually. Indeed, if we have controllability, then you do have the equality here. Yeah, indeed, it's true, because here, of course, we have a 0 B matrix, so the system is not controllable. But if you assume that AB is controllable, then in fact you have equality all the way. One can even weaken that assumption of controllability a bit more. It turns out that no controllability is even enough to prove that. Yeah. But any case, in the remainder of the lecture, we're going to work with controllable systems. And then just remember that in those cases, all of these restricted behaviors are the same. Okay, good. Any other questions about this? No? Okay, let's continue then. Great. So now, with all these mathematical preliminaries out of the way, I can start by discussing the first paper about subspace identification. I will skip for the moment the discussion of Jan Willem's paper. In fact, in that paper, there is an idea that gave rise to subspace identification, but I'll come back to that later on. So let's start with subspace identification. Okay, I consider again my linear system. I assume that AB is controllable and CA is observable. And then let's formulate a subspace identification problem. So what is the problem? Well, we have some data. So this is a restricted trajectory of the system. Again, a finite number of data points. So these are the inputs of the system and the outputs of the system on the time interval from 0 up to t minus 1. And that's a restricted trajectory of the system. So this is in B, 0, t minus 1. In addition to the data, we also have an upper bound on the state space dimension of the system. Meaning we have this number, capital N, that is larger or equal to the actual state space dimension. And this is a data-driven context, so we do not assume that the matrices A, B, C, and D themselves are known. So we don't even know their size. So we don't know the size of the matrix A. But we do assume that we have this upper bound on the state space dimension. What is the problem? Well, using this data and the upper bound, I actually want to find the state space dimension of the system from the data. So I want to find this n. Yeah, and also I want to reconstruct the system in the following way. So I want to find matrices A bar, B bar, C bar, and D bar that are related to the original matrices A, B, C, and D according to the following formulas. So A bar is equal to S, A, S inverse. B bar is SB, and C bar is C, S inverse. And finally, D bar is D for some non-singular matrix S. In other words, there exists this similarity transformation that relates the A bar, B bar, C bar, D bar system to the original system A, B, C, D.
Small n, how do you get to know? So it is known in prior?
No, small n is not known. Only the upper bound capital N is known. So the problem is to actually find small n. And so we want to find the state space dimension n from the data. That's the problem. Is that clear? Yeah? Okay. Yeah, so maybe to give some intuition of this matrix S, you may have the question, like, why don't you just want to identify A, B, C, and D from data, right? But that is never possible, actually, using input-output data. And the reason is that this system A bar, B bar, C bar, and D bar has this exact same input-output behavior as the original system A, B, C, D. And so using an input-output trajectory, I can never distinguish A, B, C, D from this bar system, A bar, B bar, C bar, D bar. Which means that the best thing that I can do, since I cannot find A, B, C, D exactly, is to find a system A bar, B bar, C bar, D bar that is similar to A bar, to the original system A, B, C, D. Yeah? So that's a problem. Do you have any other questions about the problem? Yeah?
Upper bound is for the states, like how many states it has? Or
Yes,
control.
exactly. Yes, so maybe I can go back here.
Upper bound will include all my states. You have some information.
Yeah, so for certain physical systems, indeed, you may have an idea. It's a second-order system, so this is how I choose my upper bound. But in this approach, we assume that this upper bound is given. So you need to know, indeed, some knowledge about your system. It turns out that actually, without that upper bound, you're never able to identify a system. So you really need that information. Yeah, so this is what I said. So the goal is to identify the system up to this similarity transformation. So up to this non-singular matrix S that is relating the original system and the BART system. Okay, how to solve that problem? Well, Monen and others came up with a very nice idea, but I want to start with a simple thought experiment, if you allow me. Suppose that in addition to the input-output data, also the state was given. That's of course a restrictive assumption, because in general you only measure the output of your system, but let's try to run with this idea for the moment. And then later on I weaken this. Well, if also the state is given, then I could have a look at this system of linear equations, right? So what is this? Well, let's look at this x1. x1 is of course just a times x0 plus b times u0. And so that's how I get this first line over here. And of course, y0 is c times x0 plus d times u0. So that's how I create this second line over here, right? So given, of course, the inputs of my system, the outputs of my system, and now also the state of my system, I could set up this linear equation, yeah, and try to solve for the matrices A, B, C, and D, right? It boils down to simply solving a system of linear equations. And we all know how to do that, right? So what I'm trying to stress here is that suppose that you would have the state data, this problem would be very easy. You would just solve this system of linear equations and find A, B, C, D. And that's it. But the big problem, of course, in subspace identification is that you do not have access to this state. You only have input-output data. So what to do then? Well, Mark Monen and others came up with the following approach. So let's assume that the time horizon of my experiment, so t, the number of data samples, is larger or equal to 2 times n. 2 times the upper bound on the state space dimension. Then I create this Hankel matrix of the inputs of depth 2n. So we again have 2n block rows in this Hankel matrix. And now what we do is we split up this Hankel matrix in 2 parts. So the first n block rows I call UP. So here highlighted in red. So this matrix at the top is called UP. This matrix at the bottom, so the rest of the matrix, is called UF. So I simply partition the input Hankel matrix in 2 blocks. Similarly, also for the output data, we construct the depth 2n Hankel matrix, and we also partition that Hankel matrix. And the blocks I call YP and YF. I also define matrices containing state samples, so XP and XF. And I stress again, these matrices are not given, but we can still reason with them. So let's say that the states from time 0 up to t minus 2n are given by XP, and the states from n to t minus n are given by XF. Right? Then the main theorem of subspace identification tells you the following. Let's assume that the matrix XP, UP, UF has full row rank. Namely rank little n plus 2mn. Right, because we have the n states here, and then 2n rows of inputs, so that adds 2mn to the rank. So this matrix is assumed to have full row rank. If that assumption holds, then the row space of XF, so the row space of this matrix of states, is equal to the intersection of the row spaces of UP, YP and UF, YF. So this is a great result because it tells you something about this row space of the state sequence on the basis of input and output data, right? Because this just contains input-output data, and this matrix also input-output data. And so I can find the row space of this state sequence using input-output data. Now that idea of constructing a state sequence, or the row space of a state sequence, that was already used in the paper of Jan Willems that I showed you before on the slide. But he used infinite data. And basically the idea of subspace identification was to do that on the basis of finite data. Because here we just have t samples of the inputs and outputs of the system. Okay. Well, what is then the full story? Well, you would use this theorem first to identify this row space of a state sequence. You would then construct a basis for that row space. And using that basis, then essentially you can solve the same linear equation that you have here by replacing the x by the basis that you constructed for the row space of XF. Now, so after obtaining this row space of the state sequence, again the problem is simple. You solve a system of linear equations. Yes? Yes, yes. The original system is assumed to be both controllable and observable, indeed. Yes. Yeah. Yeah. Now, there is a very important question here in subspace identification though, because if you take a closer look at this rank condition that is assumed, that you need to construct this state sequence, this is actually, yeah, sure. Exactly, exactly, because indeed, so this condition you cannot verify from the data, right? Because the rank condition that you need here involves this little n. Yeah. So that is a big problem, and that was not known at the end of the 80s how to handle that. And so it's a bit of a subtle problem, right? So, of course, this state xp is not known, and the state space dimension n is not known. So how am I going to check whether this rank condition holds, right? From the data. So to solve that problem, we go to this next paper by Jan Willems and co-authors on the note of persistency of excitation. And that paper is going to solve that question. Okay. So I now want to talk about this fundamental lemma that was developed in that paper. So again, we're going to consider input-output data. And well, the story is as follows. So I'm going to construct, again, a Hankel matrix of the input and the output. And I'm going to put them on top of each other. So this first block contains the input Hankel matrix, and here we have the output Hankel matrix. Well, the point is that if you look at these columns over here, all of these columns are restricted trajectories of the system, right? Because this data was generated by our original system. And so all of the columns that you see here are in the restricted behavior B0, L minus 1. We spoke before already about the fact that this restricted behavior is a subspace. That means that also all linear combinations of these columns are again in the restricted behavior B0, L minus 1. And that's how we can obtain the following inclusion. So if I look at the image of this input-output Hankel matrix, in other words, the space obtained from taking an arbitrary linear combination of the columns of the input-output Hankel matrix, then this image of the Hankel matrix is always contained in the restricted behavior. Yeah? That is simply a reformulation of what we did on the previous slide. But now the big question is, of course, under which conditions do we actually have equality here? So in other words, under which conditions are all restricted trajectories of the system on this interval 0, L minus 1, linear combinations of the columns of the Hankel matrix? That question is very important because it allows you to find all length L trajectories of the system from the data, simply by computing linear combinations of these columns of the Hankel matrix. In particular, to be a little bit more formal, if this equality would hold, then I would be able to parameterize all length L trajectories of the system in the following way. So U bar Y bar is in this restricted behavior of the system if and only if U bar Y bar is the Hankel matrix of the input-output data multiplied by some vector G, a real vector of size T minus L plus 1. But of course, the important question is, under which conditions do we actually have equality here? Because in general, only this inclusion holds. So to solve this question, Willems and co-authors came up with the following result. So this is their main theorem. It says the following. So let L be some integer between 1 and t. We're going to assume that the system is controllable, AB is controllable, and the input U is persistently exciting of order n plus L. Again, n is the state space dimension of the system, and L was the length of the trajectories that I cared about, right? Under these two assumptions, then, two properties hold. So first of all, we have a rank condition on the state input Hankel matrix. And so again, this is a depth 1 Hankel matrix of the state, just a row of states, right? and a depth L Hankel matrix of the input. And turns out that under these assumptions, this matrix has full row rank. So equal to n plus ml. Then secondly, the image of the input-output Hankel matrix is exactly equal to the restricted behavior. So that solves the question on the previous slide. So if you have that your system is controllable and U is persistently exciting, then indeed the restricted behavior is exactly equal to the image of the Hankel matrix of the data. Great. Yeah, and that does means, item 2, that indeed you can parameterize all length L trajectories of the system. I do want to stress that this assumption of persistency of excitation puts a lower bound on the number of data samples that you need. So an input can only be persistently exciting of order n plus L if t is sufficiently large, namely larger or equal to this number over here. You may, of course, again wonder, now here in this fundamental lemma you assume that the input is PE of order n plus L, n is the state space dimension, but maybe you don't know that. You only have an upper bound, capital N here on the state space dimension. Well, in that case, what you can do is you can apply an input U that is persistently exciting of order capital N plus L. In fact, you can show that that implies that the input is also persistently exciting of order little n plus L, and then the same statement of the theorem holds, right? So the main message is, if you don't know n exactly, you can still work with an upper bound, but you need PE of order capital N plus L then. Sorry? N? L.
Are we allowed to choose with P?
In principle, yes, but of course the persistency of excitation condition depends also on L. Yeah. Yeah.
So you have defined this persistently exciting for a function when you started. So this definition is also similar kind of thing, but you are specifying the order. So I think for a signal, you have defined the signal is persistently exciting if it satisfies some rank condition.
Yes, indeed.
Now we are just adding something of order n plus L.
Yeah.
So that k choice is now we are specifying in certain way, or how different is it in previous definition and this definition?
So the definition of persistency of excitation is the same as the one I showed you before. So what does this mean, this persistency of excitation of order n plus L, right? It means that if I look at Hankel matrix of just my input of depth n plus L, like this. This must have rank equal to n plus L times m. So full row rank. So it's the same definition as before. Does that answer your question?
Yeah.
Yeah? Okay. Yeah, sorry.
So if n is not known, capital N, we can also keep on collecting data and verifying conditions again and again. That should be able to give us. All these conditions start holding after, let's say, sufficiently large n has been reached. We can use that n. Yeah, capital N I'm talking about.
You mean to say that...
I start with some small value, some guess, random guess, smaller number. Right?
Yeah.
And I keep on increasing it, incrementing it one by one. And that Henkel matrix. That Henkel matrix.
Without knowing capital N, you can never do this. No. 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 Yeah. No, you really need the upper bound. The point is that it's not very far from verifiable from data whether this condition holds for this little n otherwise. So you really need the upper bound. But one can say a little bit more. So here, of course, in item 2, we parameterize restricted behaviors of the system. So trajectories of length L. But maybe you're also interested in just parameterizing all trajectories of the system of infinite length. So it turns out that if you choose this capital L sufficiently large, namely larger than this number little l here on the slide, which is called the lag of the system, then you can also determine B in the following way. So let's first have a look at the definition of the lag. So this lag, little l, is the smallest integer for which the rank of the observability matrix up to this power L minus 1 is equal to the rank of the observability matrix up to power L. And that's called the lag, the smallest integer for which this equation holds. And if I now choose capital L sufficiently large, namely larger than the lag, then the restricted behavior uniquely determines the entire behavior of the system. So you can find actually the entire input-output behavior from this restricted behavior. Since we can find the restricted behavior of the system here using the data in item 2, you can also find the entire input-output behavior. Just to make one final connection to the previous part of the lecture on subspace identification, we now also have an answer to the question over there. Namely, remember that in subspace identification, a rank condition on the state input Hankel matrix was very important, in particular for the choice that capital L is equal to 2 times n, right? We wanted to have then that this matrix with depth 2n n has full row rank. Now this fundamental lemma actually solves the question of, when is that satisfied, right? That is satisfied in the case that the input is persistently exciting of order capital N plus L, with L to N. So that's very nice. Okay. So I mean that in in subspace identification, you need exactly this rank condition with the choice that capital L is equal to 2 times capital M. So this one simply refers to this. Okay. Well, I'd like to show you part of the proof also of the fundamental lemma. I have good news and bad news today. I will do a proof, that's maybe the bad news. But there's also good news because I will do only one proof. In fact, I just want to prove item 1 here of the fundamental lemma, just to show you some of the main ideas.
So, is
Yeah.
there a way to enforce that the input is persistently exciting of order n plus S?
Yes. So you have to choose the input such that this Hankel matrix has full row rank, and there are different ways of doing that. You can show that to a certain extent random inputs already guarantee this property with probability 1. But you could also use impulses, for example, if you use them in the right way. But there are different ways of choosing the input such that this rank condition holds. Yeah, nice question. Okay. So to go through the... Yeah, that could be a nice idea indeed. What time is it indeed? Let's do that. Perfect.